All right, so exponential functions. We're just going to look at the exponential functions today, and then you'll do that part of the book assignment. So comparing linear and exponential functions. The growth rate is different. So linear functions, we grow at a constant rate, right? We call that the slope. Exponential functions grow much, much faster. They grow at a what we call an exponential rate, but there's a common multiplier there. So let's look at the first chart here. What's the average rate of change here? You know how to find the average rate of change between these two? Average rate of change. We have some coordinates listed here. Average rate of change is simply the slope between the consecutive points. Can you go ahead and calculate the average rate of change between the first 2 points? I think I'm right over here. So you would do 5 minus 2, and then divide that by -1 minus 0. And that will give you your average rate of change. So just calculate the slope. Yep. What do you get for the average rate of change? Three over -1. -3, yes. Let me write in that chart very easily. And then go to the next 2 points. What's the average rate of change between these 2 points? 2 minus -1 would be 3 over 0 minus 1 is -1, so that's also -3. And then -1 minus -4 is +3 over 1 minus 2 is, yeah, there's a pattern. And so as we go from point to point, we get a common average rate of change. It's -3. So we have a ratio of consecutive outputs here. The ratio of consecutive outputs from here to here, here's what I mean. Consecutive outputs would be the 5 and the 2, so the ratio of consecutive outputs would be 5 over 2, and then it's 2 over -1. Here you won't see a pattern. And then the next one is 1 over 4. And then the next one is 2 over -4 over -7, which is 4 over 7. So there's no pattern here. Would you agree? No pattern. Do you guys remember studying arithmetic and geometric sequences last year? Okay. So arithmetic sequences have a common difference, is what we call that. Common difference. From 5 to 2, there's a difference of 3. From 2 to -1, a difference of 3. From -1 to -4, a difference of 3. Okay, so it was a common D. Do you remember that? Whereas geometric sequences had a common ratio or multiplier. We're going to see that in this next chart. So no pattern there, but there is a pattern here. This is the slope. Okay, the slope is actually the common difference. So that'll connect it to something you did last year. All right, so in the next chart we've got, let's see if we can find an average rate of change. So we go 32 minus 16 divided by -1 is going to be -16. Then we go to the next one. It changes, right? So 16 minus 8 is 8 over 0 minus 1 is -8. And 8 minus 4 over 1 minus 2 is -4, and then -2. So this is no pattern in terms of average rate of change. But when I look at the ratio of consecutive outputs, 32 over 16 equals 2. 16 over 8 equals 2. 8 over 4 equals 2. 4 over 2 equals 2. So this is a common ratio. And that's the difference between a linear function, this is linear, and an exponential function. Okay, the difference between a linear and an exponential. A linear has a common average rate of change, an exponential has a common ratio of consecutive outputs. Okay, that's the difference. All right, graph of f of x equals a to the x. The graph is above the x-axis. In other words, the x-axis is a horizontal asymptote. So the graph is above the x-axis. In both cases here, whether it's exponential growth or this is actually exponential decay. So if a, the base, this is called the base, is greater than 1, it's going to grow. Okay? So if the base is, say, 2, you have the equation y equals 2 to the x, it's going to grow really fast. It's going to double every time you add another number to x. If the base is between 0 and 1, it's going to decay. In other words, you have something like a fraction like 1/2. Take 1/2 to the first, you have 1/2. 1/2 to the second goes down to 1/4, right? 1/2 to the third goes down to 1/8. So when you have a base that is between 0 and 1, or a fractional base between 0 and 1, it's going to get closer and closer and closer to 0. So the graph is above the x-axis. Also, the y-intercept is 1. Do you know why that is? Using the rules of exponents. How do we find a y-intercept? You plug in 0 for x. When you plug in 0 for x right here, what do you get? 1, yeah. Anything to the a to the 0 power is 1. So the y-intercept right here is going to be 1. So those are two characteristics of exponential functions. Okay. Now, this is assuming that we don't have a -3 or something, you know, we're not shifting it down. Okay. Well, as soon as you shift it down, it changes everything. This is not on your parent graph sheet. It would be helpful to, I'm trying to remember if we left room on there. You almost need to add this to that yellow sheet or to those functions you need to memorize. You have to add this and then also logarithmic functions. But this is what the parent graph looks like right here. This is it. All right, so we're going to talk about taking the parent graph of the exponential function and reflecting it, shifting it right or left, shifting it up or down. So it says match the graphs with the functions. Assume a is greater than 1. Okay, so these are generic parent graphs. You see the parent graph up here? A, B, C, or D? Which is the parent graph? C. C is the parent graph here. Okay, good. Now, if I take the parent graph C and I put a -2 out in front of it, what's that going to do to the function? It's going to flip it over the x-axis. Okay, D is a good guess. Yeah, let's check it. Good. What is going to happen to the parent graph, a to the x, if I put an x plus 3 in place of? What's it going to do? What's that? Grow quicker? It will. It's going to move it. It's going to shift it. Remember, if we replace x with x plus c, it's going to shift it left. Yes. So, which one do you think it might be here? A. Okay. Yep, that's right. So A shifts it left. So, if normally, okay, let me add a little more here. If normally it goes through the point 0, 1, that's the parent graph, goes through 0, 1, that's what we're saying right here, then I just shifted it 1, 2, 3 units to the left. Okay, so that's how you can get. These are tricky to graph because we don't have a ton of points to work with. We know 0, 1 is one coordinate that's going to get shifted, okay, up, down, left, or right. And then the other thing we know is that the x-axis is the horizontal asymptote for the parent graph. So if you shift it up or down, you can draw your graph based on where the horizontal asymptote goes. I'll show you what I mean on the next one. So by process of elimination here, yeah, B. So you see this -2 right here? What the -2 does is it moves this down 2 units. And that -2 takes the horizontal asymptote at y equals 0 and moves it down 2 units. The -2 in front of the a to the x, of course, flips it over the x-axis. So you reflect it and then move it down 2 units. Remember our order that we had there? We did our reflecting first, and I think we did our stretching, and then we did our shifting. So one, you can add this to your list of parent graphs to memorize. I don't think I did leave any space on the yellow sheet. You look at, did I? Okay, you could put it on the back. That's a good idea. Or just in these notes, make a note that you have another parent graph that you're responsible for. Okay? All right. The number E. Get this to Here it comes. Crazy song about the number E, ready? Yay! 2.71x2.183 is a consonant with the value of the constant E. The sum for it ranging from 0 to infinity of 1 on n factorial is B. With compounding interest, more frequently, the compounding step forms you want your balance for to be. If the number of periods approaches infinity, the limit of 1 plus 1 on n ought to be NEC. 2.71x2.1x3 is approximately the value of the constant E. It's one of 5 constants in the identity. If we have 5 plus 1 is 0, you see. Complex exponentiation means trigonometry with algebra is when you raise the match from the E. To the IX, it's plus x plus x match very equal. When we come sine x or ls set with the function e to the x is its own derivative. The natural monoration is large, the fantasy. Use rationalize to this under usually only the function of the tree and the function is split uniformly. 2.7183.
Is that our lesson? What? Is that all we're supposed to know?
Is that all you're supposed to know? Did you catch all that?
Yeah, obviously.
Good. Maybe another day. Okay, so the number E naturally arises in economics, population growth, etc. It's an irrational number in the same vein as pi. It's approximately equal to 2.718, 2818, and so on and so forth. Very useful number. Throughout even some calculus things about it. It's the one. It's the function y equals e to the x is its own derivative in calculus, which is you'll appreciate next year. It's the easiest one to remember. So you've probably come across this in your biology class. We've talked about steady state, equilibrium state of a population. 2 years ago. Okay. Well, you're given a function that so this is what we call the logistics function. You'll study this also in calculus a little bit. Logistics function is a better function than just a simple exponential function because we know that population is not going to just continue to grow unbounded, right? It's not going to continue to grow unbounded. There's going to be some kind of what we call steady state solution where it's going to go up real quickly and then level out. So what happens here is what happens is we have this function that involves e. It's going to be bounded. And we could graph it.
you're not going to need to graph it to see what happens. I'll show you what I mean in a minute. But it says the fish population in a lake at time t months is given by the function P of t equals 20,000 over 1 plus 24e to the, that's negative t over 4. Do you see the negative sign on yours? Show up better than on mine. Negative t over 4. See, let's just think about this for a minute. As time grows, so say time is 4. So time is 4. Then it would be e to the negative 4 over 4, which is e to the negative 1. You know what that means when we have e to the negative 1? What do we do with that in relationship to what's, yeah, reciprocal. So e to the negative 1. So this becomes 20,000 over 1 plus 24 over e if t equals 4. You with me? If t equals 4. So what happens to this term right here as t gets larger and larger and larger? It gets smaller. As a matter of fact, it approaches 0. That's a limit idea. And so if this, just think of this as a big 0 here then. As t gets larger, this approaches 0. So all I'm left with is 1 on the bottom. You with me? So we don't really need to graph this to see that the steady state here is going to be 20,000 because 20,000 over 1 is 20,000. So as t gets bigger, it goes like this. Here's what the function looks like. It grows really fast in the beginning and then levels out like that. Okay? So that's what the function, the logistics function, looks like. It's a very good model for population. It's a realistic model, right? Exponential might work on a small domain, but it's not realistic in the long run because supplies and space and things run out. So it says if t equals 1 corresponds to January 31st, in what month did the population reach 6,000 fish? So here's what we're going to do. We're going to plug 6,000 into P of t. 6,000 will replace P of t, and then we're going to graph this thing. So we have 6,000. I have a Windows suggestion here. So 6,000 equals 20,000 over 1 plus 24e to the negative t over 4. Now, we are going to learn how to solve this algebraically, but we need to be introduced to the logarithmic function before we can do that. So for right now, we're just going to take this and we're going to graph it. So here's what we're going to do. Go ahead and plot your graphing calculators. I'll go ahead and grab mine as well here. And pause the recording while we plot our graphing calculator. Okay, so we're going to go to the window, and here's my suggestion for a window setting. Let x min be negative 10. So x min is negative 10. X max will be 60. The x scale, how about make it 10. Okay, and then the y min, here's my suggestion. Negative 10,000 for the y min. Negative 10,000 for the y min. And then 25,000 for the y max. And then our scale had better be at least 1,000. So maybe make your y scale 1,000. So I'll give you a moment just to type all that in. And then we're going to have to go and type in this function. There's my suggestion for the window setting. The reason we're going up to 25,000 is because we know that the upper limit is 20,000, right? So we want to be able to see that line. Right now it's graphing whatever I have in here. So we have the window set. Okay, go to y equals. Clear out anything that's in there. Make sure all your statistical plots are off. We're going to type in 20,000. And then divided by, and I'm going to put it in parentheses if I'm in the classic mode here, 1 plus 24, you hit second function, and it's right down here in the first column. You'll see in blue, e to the x, it's above the ln, because those are inverses of each other. It will give you another left parenthesis, and you've got to plug in negative x divided by 4 in those parentheses, and then in the parentheses that encompass everything in the bottom of the fraction. So you have that typed, and I'll give you just 30 seconds or so to do that. If you're in the math type mode, it will have changed it over to a fraction for you. So it's 20,000 over the quantity 1 plus 24e to the power of negative x over 4. Finish your parentheses. Anybody need help with that? All right, so we hit graph. There it goes. Quick growth in the beginning, and then it's going to level out for us. Okay. And then, let's see here. If we go ahead and hit trace on here, there's when x is 25. If you want to, you can make, well, when x is 25, my y value is 19,114. What y value do I actually want to find, or p of t value? 6,000. Okay. So and we do this caveman style here, just based on the. It's not too bad. Getting closer. Okay. So it's somewhere in between 9.1 and 9.6. So we'll say right around, what's between 9.1 and 9.6? About 9.4-ish, 9.3, yeah. Is it? Okay. And you can go to the table if you want. You can go to second table. The other thing you could do is go to y equals, go down to y2, type in 6,000, then have it graph the two of those together. The red and the blue on mine, and if I find this intersection point, it will give me the x value. So to find the intersection, you go to second, hit trace, intersect is number 5. It'll ask you for the first curve, second curve. There's only 2 curves, so just hit enter, enter, and then hit enter again. It should go right to that point, and it's giving me 9.323. So 9.323. What are the units on that? What's that? No, I don't think it's fish. The 6,000 I think was fish, right? So 9.2. What? It's so t. Let's see. T equals 1 corresponds. Okay. So in what month? Okay. So first of all, t equals 9.323. So that's months. So if I'm starting, if t equals 1 corresponds to January 31st. Then what month am I in? I think you guys said it. I think you're right. So January 31st, we are in. So January 3rd. So it'd be February 31st, March 31st, April, May, June, July, August, September, October would be 9. And so we're a little bit well. November. Election day, right? Yeah, you're right. So if January 31st is t equals 1, and 9 would be, let's see, well, t equals 1 is January. Wait, so t equals 2 would actually be, wait, no, I don't know. So January, so February would be, 31st would be 2, March would be 3, April, I think it's actually October. So, because t equals 1 is January 31st. So t equals 2 would be February. T equals 3 is March, t equals 4 is April, t equals 5 is May, t equals 6 is June, t equals 7 is July, t equals 8 is August, t equals 9 is September 31st, so 9.3 would actually be August. You with me? Because t equals 1 is what? October, yeah, I mean October. You guys are looking at me funny. October, yes. So it would be October.
But we don't have that one.
Could. now. You understand it now? Counting on your fingers, that's okay. I just did. So what is the upper limit to the fish pond? On the fish pond, it was 20,000 is the upper limit on the fish pond. Okay. All right. So any questions on that? Just one example among many in the real world in terms of uses for E. Did you catch some of the other ones in the video? The banking one? What about
He
the
was talking too fast.
And he was, I know.
Yeah, I literally had no idea a single word. He needs like little closed captions. Can you read that to us?
All right. Other uses are interest compounded continuously. Have you heard of interest compounded continuously? P equals, yeah. PE to the RT power, things like that. There's lots of uses for E. You're going to see many more as we go along. We'll see some this year too. All right, so just a quick review of solving exponential functions for a variable power using same basis. So here's what I mean by same basis. Here's what I mean by same basis. Okay, this guy right here and this guy right here, if you were to factor them down using a factor tree, what would be their common base? 2. So here's what I'm going to do. 4 would be 2 to the second. You with me? And then to the 2x minus 1 power. And what would 8 be? 2 to the third to the power of x. Okay. What do the rules of exponents tell us to do when you have a power to a power? Multiply. So this is actually 2 to the 4x minus 2, don't forget to distribute it to both terms, which equals 2 to the 3x. Now, the method of same bases, what does it say? You drop the bases. If the bases are the same, if they match, you drop them, set the powers equal, and do some quick little algebra here. Add the 2 over, subtract the 3x over. So x equals 2. And what can we do to verify this? Plug it in. So 8 to the second is 64. 2 times 2 is 4. 4 minus 1 is 3. 4 to the third is 64. Okay, number 4 gets a little trickier. So you got this, okay. So, already at its common base. So I'm just going to copy down 5 to the x plus 3. Now, 25 can be written as 5 to the second. Now, one of the rules of exponents says, this is the reciprocal rule, says if you move 5 to the second up to the top, it becomes 5 to the negative second here. Now I have matching bases. So x plus 3 can be set equal to negative 2. And if I subtract 3 over, x equals negative 5. Is that true? 5 to the negative 5 plus 3 is 5 to the negative 2. 5 to the negative 2 is 1 over 5 to the 2. And 1 over 5 to the 2 is 1 over 25. Yes, it works. All right. What's the common base in number 5 here? 3. So I like to just replace in that first step. So replace 9 with 3 squared, replace 27 with 3 cubed. And then here I have 1/3 becomes 3 to the negative 1, yeah. All right, let's see what we got here. So multiplying the powers here, 3 to the 4x times 3 to the 3x squared. Now, this is always a little tricky working backwards. When you're multiplying two bases that are the same, what do you do with the powers? You add them. So when I combine this to one single base, I end up with 4x plus 3x squared equals 3 to the negative 1. So now the bases are the same. So I set 4x plus 3x squared equal to negative 1. And that doesn't quite look right in terms of what, you know, it's a quadratic equation. What do I need to do to make this look like a standard form quadratic equation? Set equals 0. And rearrange maybe, huh? 3x squared plus 4x plus 1 equals 0. Ah, that looks like something we can solve. We just spent a whole unit on that. We did solving by factoring, and if factoring doesn't work, that thing, what's that thing called? H. Q. So can we factor this? Is it factorable? What are the factors in? If it's factorable, so are there factors of 3 that add to equal 4? Yeah, 3 and 1. So what are the factors in 3x plus 1 plus 1? Good. So we don't have to use the quadratic formula. That's nice. So what are my solutions? Well, whatever I get when I solve each of those factors set equal to 0. So x equals negative 1/3 or x equals negative 1. And then I would go ahead and check each of those. I'll leave that for you to do. So. All right. I changed up the base on you here with e, but it works the same way. This one is already in its base form, so e to the negative x squared, we'll leave it alone. This one is going to be e to the 2x times 1 over e to the 3rd. It's going to be the same as e to the negative 3. Okay, now I need to combine these two together. So I have e to the negative x squared equals e to the 2x minus 3 power. Now I have matching bases on the left and right. So set the powers equal to each other. I have negative x squared equals 2x minus 3. I don't like the look of that either. So what could we do? What would you do? Yeah, that's what I would do. Yeah, move the negative x. That's exactly what I would do. And there, you know, you can move the other things to the left, but I would move the negative x squared over to the right. Hope that it's factorable. Otherwise, we got to use that h or d or whatever formula. Yeah. So, is it factorable? And what are the factors? All right, so my two solutions are x equals 1 or x equals negative 3. And then you could check them in there. It's always a good idea to check your solution. All right. So any questions on that? Okay, why don't you go ahead and plot books. I'd like you to try, it'd be good if you could try